To start our derivation of Gauss's law, we begin with a single positive point charge. The point charge has spherical symmetry. The charge produces an electric field that is radially outward and spherically symmetric. The electric field strength decreases with 1 over the square of the distance. At twice the distance, the field will be 1/4 the strength. This inverse square pattern is a key geometric feature that leads to Gauss's law. Consider a spherical surface centered on the charge. Now consider one small patch on this sphere. On this patch, the electric field is radially outward. The area vector, normal to the surface, is also radially outward. Everywhere on the sphere, the electric field vector is perpendicular to the surface, so the area vector is parallel to the electric field. The flux through this patch, then, is just the magnitude of the electric field times the area of the patch. The magnitude of the electric field does not change over the surface of the sphere. When we integrate the flux, the electric field can be factored out. Substituting for the electric field magnitude and the area of the sphere yields a simple result for the total flux through the sphere. Consider a small patch of area on a spherical surface centered on the charge. The flux of this patch is just the size of the area times the magnitude of the electric field at this point. The magnitude of the electric field is proportional to 1 over the square of the distance, while the projected area is proportional to the square of the distance. When calculating the flux, these two factors cancel, so that as the radius of the sphere changes, the flux through a patch using the same projection will be the same, independent of the radius. When one patch is projected onto a different concentric sphere, the resulting flux will be the same in both cases. The consistency of flux through areas projected from the center of the charge will be helpful in our next steps. Now consider a more general closed surface that surrounds the charge. Take a patch on that surface, noting the radial lines from the charge at the corners. For an arbitrary closed surface, such surface patches may be tilted relative to the electric field. The flux through an individual patch is given by the dot product of the electric field and the area vector. We'll be using a series of flux-preserving area projections to determine the total flux through this closed, irregular surface. First, project the patch along radial lines onto a sphere at the same distance from the charge. This projection captures the same solid angle. We can see that the surface patch is tilted relative to the sphere by the same angle that its area vector is tilted relative to the radial electric field. As a result, the dot product equals the field magnitude times the area of the projected patch. Because the electric field is radial, the projection of the original area and the electric field direction is the area vector for the patch on the sphere. Any patch on the irregular surface can be projected onto an appropriately centered sphere. The projected patch will have the same flux. We have just seen that this patch on the sphere can be projected onto another, larger sphere without changing the flux through the patches. Every patch on the irregular surface maps exactly to one patch on the sphere, each preserving flux. Therefore, integrating over the irregular surface gives the same total flux as integrating over the sphere. This integral result gives us the main result of Gauss's law. Now consider a charge located outside a closed surface. All electric field lines that enter the surface must exit the surface, providing the first indication that the net flux through that surface must be zero. Consider a patch on the surface on the side nearest the charge. Each such near-side patch has a corresponding far-side patch, which is a projection of the near-side patch. On the near side, the flux is directed into the surface, while on the far side, the flux is directed outward. The far side patch will have the opposite flux compared to the near side patch. These contributions cancel. This cancellation will occur for any patch on the near side. There will always be a canceling projection patch on the far side. If we integrate the flux over the surface by simultaneously integrating over the near side and the far side, we'll end up adding up a lot of zero. As a result, the external charge's net flux through the surface is zero. For multiple point charges, we make use of the superposition principle. The net electric field is the vector sum of the electric field due to the individual charges. Consider a surface where some charges are inside and others are outside the surface. To calculate the net flux through this surface, we add the contributions from each individual charge. For each point charge, the contribution to the net flux depends only on whether the charge lies inside or outside the surface. Charges outside the surface contribute zero flux, while charges inside contribute their charge divided by epsilon naught. We can summarize this result in the standard form of Gauss's law for electrostatics. The total electric flux through a closed surface equals the enclosed charge divided by epsilon naught.